In this video, we'll be going over the differences between displacement, distance, speed, velocity, and acceleration. In addition, we'll be looking over the different graphs using these concepts, so position time graphs, velocity time graphs, and acceleration time graphs. And we'll also be going over how all of these are related to each other, and we'll be looking at an example of all of these concepts in action using PhET's Moving Man Simulator. Hello, my name is Ritwik Jayaraman. I am a 10th grade attending Basics Chandler and currently enrolled in Physics, AP Physics C, Electricity and Magnetism, and Mechanics exams. Now, this video is supposed to act as a review of these concepts, a review of velocity, acceleration, all these graphs, in order for your test or your quizzes coming up. And these videos will be in line with Mr. Canday's Basis Physics 8 curriculum. However, these concepts, like the stuff I'll be going over, is things that will appear in other classes as well. So this video will be useful for everyone, not only if you are in 8th grade physics on basis, but also if you're in other physics classes which are going over the same material. So let's start off with going over the differences in the different terms. First, displacement. Now, displacement is how far you are from your starting point. Now, for example, let's say here I'm going to draw an x-axis. Let's say I define this as 0, this is -3, and this is 2. Now let's say we have Bob here. Hi, Bob. So Bob, let's say he starts at 0. Bob then travels to 2, then goes to -3. Now, what is his displacement? And for displacement, I'll be denoting that as delta x in this case. So delta x is going to be -3 meters. Let's say we're using meters as our units. Now, why that? It's because displacement is how far you are from your starting point. So Bob started at 0 and then finally ended up at -3, which is why his displacement was -3 meters. Now, if you looked at that example with distance, we can first define distance as how far you travel, period. Now, this means that distance can never be negative. It's always going to be something which is positive because you can never like travel a negative distance, right? That'd be weird. So, this doesn't mean that like like traveling a negative distance doesn't mean, oh, you start from 0 and go to -1. Sure, that means your position is negative, but your distance is still positive. You still travel that 1 meter. Now, if we use the same Bob example, just to clarify the differences between displacement and distance, let's first split up Bob's travel into two different parts. First, this part right here, where he traveled 2 meters, and second, this part. And in this part, he went from 2 to -3. That's 5 meters. Meaning his distance, which I'll denote as d, is going to be 2 plus 5, 7 meters. Again, distance is how far you travel, while displacement is how far you are from your starting point. Now, let's go over the differences between velocity and speed now. Velocity, you can think of it as how fast you travel with a direction, while speed is just how fast you travel. Now, to clarify this concept, let's take a new example here. Let's say we have Jimmy. And Jimmy, we're going to be using the same number axis. It's going to be going from 0 to -1. So x equals 0 to x equals -1. And let's say he does this and time equals 1 second. and there's no acceleration or anything, which means his speed and velocity will be constant. So if you go from 0 to -1, his velocity, which I'll denote as v, is going to be that displacement he travels -1 over the time, so it's going to be -1 meters per second. However, his speed, which I'll denote as s in this case. Keep in mind that this s is different from this s because this s is seconds, while this s is denoting speed. This s just looks at, oh, he traveled 1 meter over time, which is 1 meter per second. Now, again, remember speed is how fast you travel. It doesn't include a direction, meaning that similar to distance, speed can never be negative. While velocity, because it has a direction, it can be negative because negative implies a direction. Now, this distinction will be very, very useful when looking at the velocity time graphs, position time graphs, and relating that back to distance and displacement, which we'll look at later. Now, finally, acceleration. Acceleration is your rate of change in velocity. Now, what I mean by this is you can think of acceleration as your final velocity. If I say a as acceleration minus your initial velocity over time. That's what that means. You don't really need to know this equation for these concepts, but just keep that in mind that acceleration is defined as the rate of change in velocity. All right, so now that we've defined between the different concepts, let's go over the graphs now. Now, for the graphs, I'm just going to draw some basic, just some basic graphs. So let's say we have something like this. This is time. We're going to use x here. This is just going to be our position time graph. So let's say that this is just 5, 0, -5. Let's say, then let's just do something like this. Bear in mind with my bad drawing, but this is, assume all of these are straight lines. They don't have like curves or anything like that. Let's say this is 1. I mean, yeah, that's 2, and this is 4. All right. So again, this is our position time graph. Now, how you relate this back to concepts such as velocity is the slope of your position time graph is going to be your velocity. So in this case, you can see that in the first 2 seconds, he travels 5 meters along this path, which means that your velocity is just going to be your slope. So again, slope is just going to be rise over run. So it's your delta y over delta x, meaning that it's just your 5 over 2. Delta x in this case is how fast you run, right? So 2 seconds, while y is how high you climb, so 5. So 5 over 2, which you can simplify as 2.5 meters per second. That is your velocity. Now you can do the same thing for the second part. So in 2 more seconds, they go from 5 to -5, which means that they travel a total of 10 meters. So they go -10 because obviously that they go from 5 to -5, right? So that's negative. So they go -10 over 2, and that's -5 meters per second. So, and I'm going to denote this as v1 and v2. Again, this is velocity, all right? And this is velocity in these 2 different time segments. So this is velocity from 2 to 4, while this is velocity from 0 to 2. Now, if you want to find speed, that'd just be the absolute value of velocity. And what absolute value means is just it's always positive. So For example, this is how you denote absolute value. So absolute value of -5 would equal 5. That'd be your speed. All right. And now, if you want to draw the velocity time graph of this would it would just look something like this. Where you have velocity, you have time, and you had something like this. So we said that from 0 to 2, I'm just going to label my x-axis here. From 0 to 2, it was at 2.5, say. But then from 2 to 4, it was at, what is this, -5, because this is velocity. And we'll just do this. All right. So we have that. That's how it looked. And again, velocity is going to be the straight line because it doesn't change except for this one point at t equals 2. So it's just going to be the straight horizontal line. Now, if we go back to a Word document here actually and write these differences and these relationships, so the slope of your position time graph, I'm going to denote that as xt, position time graph equals velocity. Now, your slope of your velocity time graph is going to equal acceleration. And why is this? Remember, acceleration is defined as your rate and change in velocity. So in this case, if we look back at this graph here, I'm just going to circle it. If we look back at this graph, we can see that there is no slope in our velocity. Like you guys can't see any slope, right? It's a horizontal line, which means that there is no acceleration except for the 1 point at 2 seconds. But then velocity will usually be a little bit more smooth than that. And then we can look at that in other examples as well. So, and then if we look at the differences in area, so if we say, oh, what happens if we take the area under the curve, right? Now, your area under your acceleration time graph is going to be your velocity, right? Because because acceleration times time equals velocity. And then using the same concept, area under velocity time graph equals displacement. Now, why is it displacement and not distance? Because remember, velocity has a direction, right? Velocity can go under the x-axis. It can be negative. If we want to find the distance, we just take the absolute value of the area. So wherever it was negative, it'd just be positive, for example. So if I actually go back to the graphs I created earlier, let's create a new graph for velocity. Let's say velocity time looks like this. Now, your displacement would be, let's just call this A1 and A2. So the area under the curve. Displacement, which I'll denote as delta x again, is A1 minus A2, right? Because area is always going to be positive, but it's minus because this is under the x-axis. However, distance would be A1 plus A2. Does that make sense? It's like, again, remember, distance is something which always has to be positive, right? So when thinking about it conceptually, it makes sense that A1 would have to be added to A2. But in displacement's case, it can always be negative. So A1 minus A2. Now, those are the different distinctions. If we look at something more like parabolas, for example, because these are basic time graphs, and you guys will be able to figure out, oh, the velocity and the position time graph. I mean, the slope and the position time graph is velocity, for example. And when you have those graphs, it's not as hard to figure out the velocities, the positions, and the acceleration changes. However, let's say that it's a little bit more, it's more parabolic in nature. So let's say that this is our time, this is our x. Let's have, oh, whoa, bad drawing, bad drawing. Something like this. And this is parabolic shaped. Now, and let's just say this is 0, right? So now, what would you think would be the acceleration and the velocity? Well, I hope you guys have thought about it. So for velocity, it would be negative and then positive. And how do I know this? It's because you start from this point, right? You're starting from this point, and if you think about it, the x is decreasing, right? So if you were to draw a tangent line, it'd be like this. It's decreasing like this, which means the slope of the position time graph at that point is negative, right? It's going to be negative, 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 all the way until here, where it'll be 0, velocity will be 0, and then it'll continue increasing, increasing, increasing. Now, that means that velocity is negative, then 0, then positive. And what about acceleration? Acceleration is going to be positive in this case. And now let's think about the relationship between um, acceleration and velocity, right? Of course, acceleration can be negative. It is a vector. So actually, let's type that out here. Acceleration and velocity are both vectors, meaning that if they are in the same direction, that means you're increasing speed because acceleration and velocity both they'll be both coordinating with each other. They'll be working with each other. Let's think of it like this. If we'll use the basic kinematic equation, Vf equals V naught or V initial plus acceleration times time. If your acceleration and your initial velocity are in the same direction, your velocity, your final velocity is going to also be like bigger, right? And remember, speed is the absolute value of velocity. So for example, let's think of it like this. If your initial velocity is -3 and your a is -1, right? Let's say you do this and your t is 1 second. Now, if you use this equation, -3 plus -1 times 1, -4, right? And you can see actually your even though your velocity has gotten more negative, your speed's gotten more increased, right? Your speed's increased because speed is just the absolute value of velocity. That's a distinction which you guys need to get down because it's very important. If you guys don't get it down, it'll be very confusing. Know your differences between scalar and vectors and how that applies to distance, displacement, etc. And then if we just switched up the sign here, if we said A was actually positive, it'd be 3, -3 plus 1, 1, right? Should be -2. And you can see now that speed is decreased. It was supposed to be 4, but since our acceleration is positive now, it's now at -2. I mean, it's now at 2, sorry, because speed is always a positive quantity. So you can think of here as just like nailing this in. Speed in this case starts at 3. Let's say our units are 3 meters per second. So speed initial, but then when you take speed final, it's going to be 2, right? Again, speed is the absolute value of velocity. I cannot stress that enough. But then your velocity would start at -3 and would end at -2. Again, I'm deriving all this from the equation Vf equals Vi plus At. Now, hopefully that gave you a basic review of the differences and the relationship between displacement, distance, velocity, speed, and acceleration. And we looked at the graphs, and we've actually looked at here, now going back to this example, that velocity starts out negative and then goes positive, but acceleration in this case, if we assume that this is just a basic parabolic curve, will be positive. Now, how do I know this? Again, remember, when velocity and acceleration are acting in different ways, speed is going to decrease, right? So the absolute value is going to decrease. And we see that happening here. Velocity starts out negative, but then acceleration starts out positive. That means the velocity is going to slowly go down to zero, which it does here. And then since the acceleration always stays positive, velocity will start going up, will start increasing at an increasing rate, which is why you get this curve here, which so again, the slope increases at an increasing rate. So like for example, velocity is, let's say that's 1 meters per second, like that slope there is 1 meters per second at this point. Here, let's say it's 5 meters per second. So you can see that it's increasing. And again, this agrees beautifully with our statement that if velocity and acceleration are in the same direction, your speed will increase, but if they're not, speed will decrease, right? And you guys can see that here. Since acceleration is always positive, when velocity starts out negative, your speed's decreasing until it reaches zero, right? Once it reaches zero, velocity starts becoming positive, acceleration is also positive, so speed will increase. Now, let's tie this all back together with Fett's moving man simulator. So here we have Fett's moving man. If you guys are in Mr. Kennedy's class, you probably have already done this. But Fett and their simulations in general, just as a side tangent, are really good and help you visualize these physics concepts. So what I'm going to do is, let's say I start at -10, okay? So position is going to be -10. My velocity, remember velocity has a direction, so that's why there's this velocity vector here. Same thing with acceleration as a direction, so we have an acceleration vector. Let's say my initial velocity is 0, but my acceleration is 1. Now, I want you guys to see what happens to the man as time progresses. So I'm going to play it, and those are the arrows that display the acceleration and velocity. The green arrow is acceleration, while the red orangish color is your velocity vector. Now, what happened there? You can see that as the moving man progressed along this meter stick, right? Along this, like whatever you call it, right? This position. As he progressed and as time progressed, he got faster, right? Let's watch it again. Again, going -10. Let's make our acceleration 1. And the link to this simulation will also be in the description of this video if you guys want to play around with it on your own time. See, he's starting slow, but he's getting faster and faster and faster and faster until he eventually reaches his destination, right? And you guys can also see velocity there was increasing. Started at 0 and 0, but by the time he got to the end, it was around 6 point something, right? Now, and it again shows that when velocity and acceleration are in the same direction, your speed's going to increase, right? Now, finally, let's tie that back into the chart. Let's say position is going to be, let's say our position starts at -10 again. And let's use the same example. And let's see what happens. As you see, he starts off slow, but he's going to be faster and faster and faster and faster until he reaches his destination, which is going to be that 10 point. All right. Now, don't worry about these like sudden dips. That's just because he's hit a wall, so that's the end. That's why his acceleration is so negative, and his velocity has just all of a sudden gone to a halt at 0. Don't worry about that. What I want to worry about is these curves here. I want to explain those actually. So position is going to start like this, and it's going to keep increasing. And you guys can see actually how it increases, the slope of the position time graph increases at an increasing rate. And this agrees beautifully with what we had here in this example of, because velocity and acceleration are always in the same direction. Don't worry about this -75.5. Again, that's because he stopped. Remember, it was at 1. So if I can actually zoom in here, you can see how it was, that's at 1. And you can see how velocity is a constant line. It has a constant slope because again, slope of velocity time graph is acceleration, right? So this slope will actually be 1 meter per second squared. And now going back to a position time graph, you can see how it starts increasing, because again, velocity and acceleration are in the same direction, which means your speed will be increasing. And now just to tie that all back in, just as a nice tidbit, if you have something like this, something that looks like a smiley face, that means your acceleration is going to be positive because, as we explained before, your acceleration is helping slow down that velocity, helping it go to zero before velocity and acceleration are in the same direction again, which means that velocity will go increasing, and speed will also increase as well. But then if it's like this, acceleration is negative. Now, you guys should pause the video for a second and think about why that is. And after that 1 second, I'll explain why acceleration is negative when it kind of looks like a frowny face. Now, I hope you guys have thought about it. And if you said acceleration is negative because first velocity is positive, but then it decreases and it goes negative, then you're right. Because again, this is a position time graph, right? When I mean, not acceleration, velocity starts off at this really positive value. Like if we did a tangent line here, you guys can see this the slope of the position time graph at that point is really high, right? But it's steepening. It's actually like it's becoming a little bit more less, right? The slope is becoming less and less and less, signifying that the velocity is becoming less or the speed's becoming less. And that's because the velocity is positive and acceleration is negative. But then as we get to this other side, and again, there'll be a point where speed and velocity are zero. But then as we get to this other side, you'll see that velocity will start going negative. Acceleration is also negative, so velocity will keep going decreasing, meaning that velocity is going to be a more and more negative value, while speed is going to be increasing, which is why you can see that this slope decreases at a decreasing rate. Now, does that all make sense? Again, Fett's moving Mansomer is a great way to illustrate these concepts. I'll go over one more example actually. Let's say that we start at zero, right? Start at zero, say our velocity is 2, but then let's say our acceleration is -3. Let's see what happens now. That actually may be a little bit too close. Let's say acceleration is -1, and let's say we start at 2. That looks a little bit better, and we'll wait for the simulation to finish. So yeah, you guys can see now how he's like the man's getting faster and faster. His speed's increasing because his velocity and acceleration were in the same direction. Once it got to this point where velocity hit zero, um and then position, as you guys can see, has this kind of like McDonald's arch, right? Where it's starting to go positive because velocity initially is positive. It's not zero yet because acceleration hasn't kicked in for that long. But then once as time progresses, acceleration being negative will cause velocity being negative, and then the man will increase his speed until he hits that left wall over there. And again, this that position graph looks similar to this, which is similar to this thing here, which shows that acceleration is negative. Again, this assumes constant acceleration though. Now, I hope that all made sense. Again, just as a quick recap, displacement is how far you are from your starting point. Distance is how far you travel, period. Um, Velocity is how fast you travel with the direction. Speed is how fast you travel, period. And then acceleration is your rate of change in velocity. Now, displacement, remember, is a vector. Actually, we can say this, right? Velocity is a vector and acceleration is a vector, while speed and distance are scalar. They don't have a direction. Then we looked at the difference in the position time graphs, velocity time graphs. And then the acceleration time graph, so we know that the slope of your position time graph is velocity, slope of velocity times acceleration. The area under your acceleration time graph is your velocity, while the area under your velocity time graph is your displacement. And actually, the absolute value of area under velocity time is your distance. And again, we explained that because distance can't be negative. It is a scalar quantity, which means that when you do these things, when you add the distance, it's going to be a1 plus a2, right? But for displacement, it's going to be a1 minus a2. Finally, we looked at how when acceleration and velocity are in the same direction, that's going to increase your speed. So whether that's negative, negative, or positive, positive, and when they're in different directions, that's going to decrease your speed. So differing directions decrease speed. And we showed that all using Pet's Moving Man Simulator, but also using just a few examples here. So I hope that all made sense. If you guys have any questions, feel free to leave them in the comment section below, and I'll respond as soon as possible. Thank you guys so much for watching this video, and as always, leave a like, subscribe to Brillianaire's YouTube channel. More of these videos will be coming out soon regarding different physics topics, different and other subjects as well. So hopefully we're going to be getting math and all the different sciences up soon, etc., etc. But yeah, thank you guys so much for watching, and I'll see you guys later.